0.1 kilogram copper cup contains 0.8 kilograms of water at 20 degrees C. 20 grams of ice whose temperature is negative 10 degrees C is dropped into the cup. Determine the final temperature of the system. This is a calorimetry problem involving heat flows. And we have two formulas for heat flows. One of them is the formula for the amount of heat that flows while some material stays within a single phase. This one is mc times the change in temperature, sometimes known as the MCAT formula. And the other one is plus or minus mass times latent heat. The second formula requires a little bit more effort, as it doesn't take care of the sign automatically. The situation that we have at hand involving multiple objects, cup, water, and ice, coming to a final equilibrium is one in which we consider that we have an isolated system. What this means is that the total heat flow of the system is going to be equal to zero. The reason is that for every heat flow out of any one object, that heat must be entirely accounted for flowing into the other objects. So all of the negative Q's add up with all the positive Q's to give us a total of zero. Our job is to be meticulous in writing every single term of interest in order that we can get the problem correct. So let's begin with the cup. The copper cup begins as a solid at 20 degrees C and then moves to some final temperature. We'll presume that the cup remains solid during this entire process, therefore we use the formula within a single phase, so we'll have mass of the copper times the specific heat of solid copper times the change in temperature. Change in temperature, as always, is final minus initial. We don't have the final temperature, so we just put in T final for that variable, and we know that the copper begins with an initial temperature of 20 degrees. You might think about this formula for a moment. We use degrees in Celsius rather than in kelvins. That's perfectly good because the formula itself contains a delta T, and differences in temperature are the same number regardless of whether you're using Celsius or Kelvin throughout the problem. Since we finished with the copper cup, let's move on to the water itself. Now, since there's a large amount of water, 800 grams, and a small amount of ice, only 20 grams, I'm going to assume that all the ice melts. This would mean that the water itself stays within a single phase, so I would have a term which is mass of the water, specific heat of water, times final temperature minus initial. Notice in both of these formulas, I have always included the heat as a positive term. The reason is that the delta T will automatically take care of the sign of the overall heat flow for me. Next, let's deal with the ice. Unfortunately, most textbooks, in an effort to make simpler problems for the students, actually wind up teaching students something that is incorrect. Your textbook may wind up accidentally teaching you that the temperature of ice is 0 degrees. That's incorrect. Ice exists from any temperature of minus 273 Kelvin, which is absolute zero, all the way as high as 0 degrees. In this problem here, the ice begins at a temperature of negative 10. So as we imagine the happenings on the ice, the first step is that the ice must raise its temperature to 0 degrees before it can begin to melt. Since this will be change of the ice within a single phase, in this case the solid phase, we'll again have the mc delta T formula, where we'll have mass of the ice, specific heat of ice, times temperature final minus temperature initial. Since we're only dealing with bringing the ice to 0 degrees, that temperature final will be 0 minus the negative 10 degrees of the starting point. Next, we need to melt the ice. This is going to be a phase change, and so we're going to have to turn to our mass times latent heat formula. As always, this formula does not automatically generate the right sign. It's up to us to insert the appropriate sign. Since we recognize that ice going from solid to liquid form involves heat flowing into the ice, that will be a positive heat flow, and so we select plus mass of the ice times a latent heat. Still not done, we need to select which latent heat. Our choices are latent heat of fusion or latent heat of vaporization. Since we're going from solid to liquid, which is the same number as going from liquid to solid, we'll be using the latent heat of fusion. Finally, the last term is actually the most likely one to trip up students in terms of formulating it correctly. We need to take this now melted ice from 0 degrees to the final temperature in order for the system to be at overall equilibrium. Well, that's going to be within a phase change, and so we will call upon the MC delta T formula, which, as always, yields its own sign. So we will use plus mass of the ice times specific heat of water. The reason water, this ice is no longer frozen, and as we raise its temperature further, melted ice is now water. That's the most common error that students make in formulating a problem like this, is they don't recognize that once the ice has become melted, it is now water, and the appropriate specific heat to use is the specific heat of water. Finally, let's put in the change in temperature. This is water at 0 degrees moving up to some final temperature. So temperature at the end of this part minus the temperature at the beginning of this part, which is 0, yields this formula. As written, there is one and only one unknown in the equation when we include the 0 at the other side of the equal sign. That one and only one unknown is the final temperature. However, there's a lot of terms, so please be careful with your algebra at this point in the problem. Searching for the easiest way forward, as any mathematician would do, we're going to set 0 equal to two terms. One term will be the collection of all things that are multiplied by temperature final. So we will have temperature final times a long quantity. This quantity will include the mass of the copper times the specific heat of copper, plus the mass of the water times the specific heat of water, plus the mass of the ice times the specific heat of water. The second term is the collection of everything else. And with a little bit of foresight of the fact that I'm going to need to move this term to the left-hand side of the equation, I'm going to factor out a minus sign so that I have the following set of quantities. I'll have 20 times the mass of copper times the specific heat of copper, plus another 20 times the mass of water times the specific heat of water, minus 10 times the mass of ice times the specific heat of the ice, minus the mass of the ice times the latent heat of fusion, and that's all. Because we had the foresight to pull out that minus sign, the next step in the problem will be quite simple. The temperature final will be equal to the ratio of two rather large quantities. In the numerator is the term that was not multiplied by the final temperature, and in the denominator is the other term. We'll need to consult our textbook to learn all the specific heats. The specific heats of ice, water, steam, and copper are 2050, 4186, 2080, and 386 joule per mole Kelvin. The latent heat of fusion for our water is equal to 334,000 joules per Kelvin. Plugging all these numbers that we know, as well as the masses, into the previous formula yields, with careful algebra, the final result: 17.5 degrees Celsius, refreshing on a hot day.